Okay, with this lesson, we're going to get into section 5.3 on definite integrals. And before we do this, I want to just kind of summarize where we've been so far, because the last several sections have been sort of disconnected. Um, really going all the way back to section 4.8, where we did the indefinite integrals, which means antiderivatives. So we did that section, and then we started chapter 5, and all of these have seemed kind of separate. It seemed like kind of separate topics. We did the antiderivatives, then we moved on in chapter 5. We talked about estimating area under functions using rectangles. In 5.2, we talked about sigma notation and sums. And so these three seem pretty disconnected. I did show you sort of a connection between 5.1 and 5.2 if you watched that video, where I talked about how the um, sigma notation can be used to represent what we're talking about with the areas of rectangles, and then what happens when we let the number of rectangles go to infinity. So we saw a little bit of connection here between these two topics, but they haven't been connected at all to these antiderivatives. So this is what we've seen recently. What this lesson is about in 5.3 on definite integrals. Um, Here we're going to talk about finding the exact area under a function. And so this automatically kind of connects to this idea of area, area under a graph. And again, in 5.2 in those lessons, we made sort of a connection to exact area as well. So this will kind of bring these concepts together a little bit more, but I'll introduce some notation to you that we haven't seen for something called a definite integral. And just the fact that I'm calling these integrals will start to connect things back to 4.8. And then finally, in the next section, 5.4, the fundamental theorem of calculus, will take all of these ideas that we've been talking about, and they'll all kind of converge to this theorem in 5.4 called the fundamental theorem of calculus. All right, so this is kind of where we're headed. With this lesson, though, let's just focus on what definite integrals are about and what their notation looks like. All right, so a definite integral, you still have this integral notation like we had with the indefinite integrals back in chapter 4. The only difference is we have some numbers, a and b. So a and b are just numbers like 0 and 4 or 1 and 7. It's a and b will just be some numbers attached to this integral sign. Whenever you have these numbers a and b attached to the integral sign, that tells you you're doing a definite integral, as opposed to something like this without the numbers attached to the integral sign, which is an indefinite integral. Okay, so we did these indefinite integrals in 4.8. But here, when we're doing a definite integral with these numbers attached to the integral sign, the way I would read this notation is I can say something like the integral of f of x from a to b, and then this dx tells us what variable we're working with. So we can say we're doing the integral with respect to x. And I mean, you don't have to say it word for word like that. You could switch things around a little bit. You can say that you're doing the integral from a to b of f of x with respect to x. But generally, you're going to be saying something roughly like this whenever you read this out loud. A and b, like I said, are just numbers. We call those the bounds on the integral, where a, we refer to that sometimes as the lower bound. B, we refer to it as the upper bound. Now, what the integral means, whenever you see this notation, this integral represents the exact area under the graph of f for x values between a and b. Okay, so the notation, whenever you see something like this, it's telling you you have some function f of x, and it's asking you, whenever you see this definite integral notation, it's asking you what's the exact area, not an estimate like we did with the rectangles, but what's the exact area under this function between a and b. All right, so if I've got some function f of x, and I've got these x values a and b, if we look at this region between a and b, whenever I ask you for the area of this region, the area of this region is exactly what we mean when we ask you to evaluate one of these integrals. So when we do these definite integrals, the answer that we get out from these definite integrals will be some number. Okay, so there's a big difference here. When we did these in chapter 4, these indefinite integrals, our final answer was some function, right? We were doing an antiderivative, and we got some function out. These, our answers are going to look completely different. Our final answer is just going to be some number. And the number that we get there is going to be the number that represents this area under your function between a and b. All right, now let me just show you one simple example here. And then in the next video, maybe I'll do a few more examples and talk a little bit more about the properties of these definite integrals. All right, so one simple example. Let's say y equals x. Let's do the integral of this function, the integral of x dx, and let's do this from 0 to 2. So first of all, this function that we're dealing with, x, let's think about what the graph of this thing looks like. We know that y equals x is just the diagonal line. And if I want the area under the graph between 0 and 2, then when you see this notation, the integral from 0 to 2 for this function y equals x, with respect to x, it's asking what's the area under this graph. Now in this case, y equals x is a nice straight line, and so I can answer this using basic geometry formulas. All right, I don't have to come up with an estimate like we did with the rectangles a few sections ago. I can tell you the exact area because I know how to find the area of a triangle, right? I know that the area of a triangle is 1/2 times base times height. All right, so if I know the base and I know the height of the triangle, then I can find the area. Well, the base is obviously 2. The height, well, that's whatever this y value here is, but this is the function y equals x, so that's the y value 2, so the height is also 2. All right, so in this case, the area of that triangle is 1/2 times 2 times 2, which is 2. So if I can use basic geometry to find the area of this triangle, then I've also done this definite integral. The integral of this function x from 0 to 2 with respect to x, the exact area under this function is 2 for x values between 0 and 2. All right, so that's one simple example. In the next video, I'll give you a few more examples and we'll see how some properties of definite integrals work out.